everybody, I'm back and I did make a mistake. I copy pasted the new PowerPoint to from the old PowerPoint, so it has the wrong title. This is probability part 3b, and we're going to talk about independence. Sorry for the typos. I'll try to fix that as we go forward um, on all the other documents that matter. Okay, so independence, and it makes sense if the two probability events A and B are independent, then if B has already occurred, that shouldn't change the probability of whether or not A occurs, right? So we need this idea of A given B, and that's how we pronounce it, or that's how we say it. We use a vertical line between the two event sets, and that's red, the probability of A given B. And it means if B has already occurred, what's the probability of A given that B has already occurred? And it's called conditional probability, right? We're finding the conditional probability that A is happening, right? Conditioned upon the fact that B has already happened. Okay. And the formula for the probability of A given B equals the probability of A intersect B divided by the probability of B. And what you'll notice is that we basically are restricting the probability space, right? The denominator, the probability that B happens, right? It rules out all of the other outcomes that could have been true, right? The only things that can be true are the things in the event set B. And whichever of those are, also in A, right? That's the numerator. So that's how this is working. Also, if A is independent of B, then B is independent of A, right? So the two sets are either independent or not. We don't have um, independence for one and not for the other, one way and not for the other way. All right, so let me get rid of these stray marks and move forward. Okay, so this is our definition, right? That A and B are independent provided, right, that the conditional probability of A given B is equal to the probability of A, right? B happening didn't change A. That's exactly our definition, which I circled in red. And as I pointed out, if A is independent of B, then B is independent of A. So it works in either way that I'd like to do the formula. And I've said that about 6 times now. But um, so we have example 1 here. We have a coin flip coming up tails and a dice roll coming up 4. Are events T and F independent? And what this comes down to, right, is the intersection of T and F. I think it's pretty clear just intuitively that these should be independent. Why? Because whatever the dice roll was shouldn't influence the coin flip, and whether the coin came up heads or tails shouldn't influence the dice roll, right? And it turns out that yes, there are no outcomes in the intersection, right? So this is the good example. When I have two probability experiments happening side by side and they're independent, I can just multiply the probabilities, right? So there's a 1/6 chance of getting a 4 and a 1/2 chance of getting tails. So I can multiply 1/4 times, 1/2 times 1/6 and get 1/12. That's the probability that this happens. Let me get rid of the stray marks. Right, and we can jump into our correctly named notebook here. Okay, and right, so what do we have? We have that the probability, right, of T union F. I'll just put that in, I'll comment that out, right? What are we doing here, right? The probability of T union F, right, is 1/2, sorry, 1/2 times 1/6, right? The probability of T is 1/2. The probability of F, the dice roll coming up 4, is 1/6, right? They are independent. Okay. And these are two independent probability experiments, so we're multiplying, not adding. So it's not quite the same formula that we're looking at with inclusion, exclusion, and that's an important point to draw. The second example on the slide was given a fair dice roll. We have W as the probability that the value is divisible by 2, and R be the event that the value shown is divisible by 3. Well, okay, this is just going to take some checking. So W is the set, right? With a 2, a 4, and a 6 in it, right? And then, sorry, some hashtags to comment this part out are is the ones that are divisible by 3, which I hope you'll agree will be just 3 and 6. Okay. So the question is, are the events R and W independent? And the answer is no. Why? Well, the main answer is because this intersection is non-empty, so we're going to have a slightly different thing. But let's actually check, right? We do have a formula, and we can check. All right, so the probability of W given R, okay. Um, well, if R has already happened, the probability of W happening is 1, right? Because it can either be, we know that it's either a 3 or a 6, but there's only one outcome in R, right? Excuse me, in W. That's also in R, right? But, right, the probability of W is 1/2, right? So the probability of W is not equal to the probability of W given that R has already occurred. So are they independent? The answer is no. Okay, so let me put some comments in, some hashtags in there. And then my answer, right, is going to be no, not independent. All right, now the next example on the PowerPoint has a graphic here. So it was basically, this is a teaching tool called a geoboard, right? And these are rubber bands. This is an actual tactile instrument that we can take into a elementary or middle school classroom to help learn some geometry concepts. All right, but the blue shaded area is has a probability of 20 out of 100. And notice that every single one of these squares is equal to 1 square unit, 1 unit of area. And the green shaded area is 40 out of 100, and the red shaded area is 12 out of 100. And the question is, are the events green and red independent? What about B and G? Blue and green. What about red and blue? Okay, so let's jump in and try to sort this out in the notebook. Okay, so we have everything we need here. Okay, and in the comments, I'm going to remind myself that blue is equal to 40 over 100 and that red is equal to 12 over 100 and green, sorry, this one's green. Green is equal, and blue is equal to 20 over 100. And I'm using unreduced fractions again, just because that will help us see the area. This is very much an area problem, right? So I'm keeping them together. Okay. And then let's look at it. The geometry actually helps us a good bit here. So let's look at this. What's the probability of blue given red, for example? Okay, so if we're going to do blue given red, well, if red has already occurred, we're in here. And how many of the things are blue? Just these top two. So let's see. There's 12 minus 2. Interesting. Okay. So the probability of B given red, right, is equal to what? 2 over 12, which equals 1/6. Let me go back up here and get that right. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's 2 out of 12, or sorry, 1/6. Okay. Which is not equal to blue, right? The probability of blue, so I'm going to go, but the probability of blue is equal to what? It's equal to 1/5. Okay. So probability of blue, given that red has already occurred, is 1/6, but the probability of blue is 1/5. So R and B are not independent. Okay, well, that's interesting. So let's look at some others. Let's look at probability of blue given green has already occurred. All right, so what's that? Sorry, equals. Okay, well, getting rid of some of our marks here. And okay, so now if we know that green has already occurred, we're looking at this rectangle, of which this many are blue. Okay. So again, this is why the unreduced fractions help. I know that there are 40 square units in the green, and 1, 2, 3, 4, 5, 6, 7, 8 of them are blue. Okay. So I know that that probability of blue given green is 8 divided by 40, which equals 1/5. Okay. And the probability of blue is just what it was above, right? It's 20 over 100, or 1/5. So R and G are independent. Okay, and again, it comes down to, and this is why I like the geometric picture, right? It comes down to this ratio of areas, right? We're restricting the sample space to just what has happened, and here just the green had already happened. We knew that it already occurred, so we've restricted our sample space to just the green shaded squares. And of those, these up here were the ones that were blue. And it turns out that they're just the right fraction of the green. The blue shaded is just the right fraction of the total green, that the probability is the same. And therefore, they're independent. Okay. Getting rid of the stray marks here. Right. And then what about, let's see. So we did blue and red. What about green and red? Okay, we can do green and red. Probability of red given that green has already occurred. Actually, let's do it the other way. Let's do it green given that red has already occurred. Okay. So if red has already occurred, we're looking at these 12, of which 1, 2, 3, 4, 5 are green. So the probability of green given red is 5/12. But the probability of green is 2/5, right? Um, 40 over 100 reduces, since both numbers are divisible by 20. 40 divided by 20 is 2. 100 divided by 20 is 5. So 2/5 and 5/12 are close, but not the same. So we know that, sorry, and then I made a mistake here. Blue and green are independent from above. So red and green are not independent. Okay, so again, that's why I brought the pictures with color, so you can kind of see the geometry, right? The independence of two sets doesn't mean that they don't have an intersection or that the intersection is empty. No, it means that if there is a non-empty intersection, then the ratios work out perfectly. Um, so it's still a rather strict requirement, but you can see how that works. All right, and then jumping back into our slides, we have three more. Given a standard deck of 52 playing cards, determine if the following sets, event sets, are independent. Drawing a heart and drawing a queen. Now this is interesting, right? Drawing a heart and drawing a queen. Why? Because they are independent. Why? Well, what's the probability of a queen drawing a queen given that you know you've already drawn a heart? Well, there are 13 heart cards, and there's one of those that's a queen, so 1/13th. Just like drawing a queen is the probability is 4/52, which reduces to 1/13th, right? So let's jump back in here for this example, right? So the probability of a heart equals 1/4, right? And the probability of a queen equals 1/13th. And the probability of a heart, let's just call that intersect, Q, right, is equal to, um, actually, I should be doing the cardinalities. Well, that'll do. That'll do. And put in some hashtags to comment this out, right? Um, okay. And then to answer the question, right, we have, right, the probability of H. Let me do Q given H. Probability of Q given H. Well, if hearts have already occurred, I know that one of them is a queen, so that's 1/13th. And the probability of Q is equal to 1/13th. And I'm not going to write that out. We clearly have independent sets there. Also notice that it works in the other way around. If I do probability of, sorry, of heart given queen, right? The probability of heart given queen, well, if I draw a queen, there are four of them, four possibilities, right? One of which is a heart, right? I have the queen of hearts, the queen of spades, the queen of diamonds, and the queen of clubs, right? Um, but the probability of hearts, right? There's one suit, hearts that has 13 cards out of 52, and 13 over 52 does reduce to 1/4. So notice that the independence works either way I try it. I can do probability of queen given heart or probability of heart given queen, and both of them show independence by the formula. The events of drawing a spade, drawing a jack, and drawing a face card. Okay. Um, so what do we have? Right, the probability of S is equal to 1/4. Okay, and the probability of J is equal to 1/13th. And the probability of face card is equal to, well, how many face cards are there? Well, there's three of them. The saying amongst card players is aces don't have faces, right? So the face cards are jack, queen, and king. So there's three of them, but there's four suits, right? We have the hearts, the clubs, the spades, and the diamonds. So there are 4 times 3, which means there are 12 50 seconds, which reduces to 6 over 26, which reduces to 3/13. Okay. And opening up some more lines, right? So drawing a spade and drawing a jack. Notice that that is exactly the same as drawing a heart and drawing a queen. It's just a different value and a different suit. But we found out that these were independent. So spade and jack, those are also independent. Okay. Drawing a jack and drawing a face card, that won't work. Why? Because the probability of drawing a jack is 1/13. But if I know that I've already drawn a face card, it's 1/3, right? So J and F are not independent. And what about S and F? Well, it turns out those are independent. And you can double check that to see. What about drawing a red card and drawing a face card? Let me explain that right here. Right, we can do it real quick. Right, so the probability of red is, and let me just use 26 over 52. We'll have the actual number of objects represented, and then the probability of a face card, right, like we said, is 12 over 52. Okay. And then the question is, what's the probability of F given R? Well, the probability of F given R is what? Well, if we have red cards, we're down to 26, and there are 3 face cards, but we have 2 suits that are red, the diamonds and the hearts. So 2 times 3, that's 6. So we have 6 divided by 26. Okay. Well, so let's reduce a little bit to see, right? Because is 1252 the same as 626? Well, yeah, if I divide both the 12 and the 52 in half, you can see that, right, that events F and R are independent. Okay, so that's how the definition of independence works. That's the formula we use to verify it. And you definitely want to double check these. They can be counterintuitive, again, because it comes down to ratios inside the restricted sample space. Sometimes it's not necessarily intuitive which things are independent and which things are dependent. So please use the formula and check. All right, have a great day, everybody. I'll see you with the next section.